Hello viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about the current hype of the town, China supercritical CO2 turbine. So let's dive deep into it. Now I'm going to assume you have watched my channel. I have covered this years ago and I even covered one of my visit where I had hands-on on it. So let's dive deep into it. So why CO2? Well, here's the deal. Given the constraint of Earth's environment, basically pressure and temperature, CO2 is one of the best gas thermodynamically. There are other gases that have this better or that better, but this is thermodynamically one of the best, meaning it is super easy to achieve supercriticality. And let this be very clear, supercritical CO2 is a normal thing. In industry, it's like, shut up, take money, go, don't bother me, that kind of thing, meaning we use it for a lot of things, including food. So it's a known sorted technology. So temperature and pressure that we have to deal with, it's not bonkers. And what do we mean by thermodynamically best gas? Well, density is really high, specific heat capacity is good, and critical point is very decent. So you are looking at like atmosphere, 73 atmosphere of pressure you need, like 73 bars give or take, and temperature only 31 degrees Celsius, and you will achieve supercriticality. So again, that number may not make sense. Okay, what is 73? Is it high or low? And what is 31? Is it high or low? Let's compare it to water. So water goes to 218 bars and 374 degrees Celsius. Yeah, then you achieve supercriticality. So fundamentally, let that be very clear. Can we achieve supercriticality with steam? Yes, but it is fundamentally far more difficult. CO2, it's not that brutal, so to say. So that's why people are so interested about CO2. Can you replace with other gas? Yes, but none of them have the sweet spot like this. Another aspect is people are attracted to this simply because it can. It's not like it has done that, is done verified, third-party verified and all that. No, it can cross 50% thermodynamic conversion efficiency. Be mindful, normal coal power plant can generally 35% or 30%. Some can go higher, but they are more expensive, but they can go higher, but 30 to 35 is like average, so to say. So 50% is significant improvement, meaning if your coal power plant is using this technology, you will consume far less coal. Even the output will remain the same, but coal consumption will go down, which again has dramatic benefit. First, you save money. Corporations like to save money, so they enjoy. Secondary benefit, less pollution. GG. So that's why people are attracted to it. And why I was very optimistic about the technology, it can work without drinking water. Right now, what you have is water going through phase change, and to condense that water from steam to liquid again, we run it through a secondary loop. Let that be the water that is going into turbine that never leaves from here. So that is completely closed loop, because again, that's a very high purity water. So they generally keep it in closed loop. This water is what happens to cooling water that is used to condense it. And again, because Earth is hot, and India is very hot, we basically have to boil rivers away to keep coal power plants cool. And again, that is true everywhere. That is so true that in peak summer heat of 2022 or 2023, France had to shut down a nuclear power plant because they were boiling the rivers away and they had a drought crisis, so they had to shut it down. So again, water cycle is also brutal. So having a system that does not require to drink water, that's good. That's good. And it's super small for his power. For example, this lady, I have the luxury of knowing these people because venture capitalist Minik Gorgi is working with them and I am working with him. So this is in Texas. So this lady is handling something that is 10 megawatt. Like, whoa, it can't be that small. It can be. It's very easy. Like you go into turbo machinery of rocket engines, they're like, bruh. That's a nice puppy, nothing more. Look into the turbine horsepower of basically RS-25 engine. Then you will understand. The RPM is very high. That's why it's so small. Basically, shrink it down by increasing the RPM. So that's the CO2 part. Now, let that be very clear. If you want to understand what does it mean to say supercritical, I found one YouTuber. I'm going to take his explanation. It's the best explanation I've seen. Whenever you are talking about liquid, you are talking about two molecules or elements generally getting so close to each other, they have a stiction to it. It's like, basically, and that's why you have to dump heat into the system so they vibrate enough to break through it. Boom. So when you're talking about H2O, why H2O is liquid in normal scenario? It does not have enough wiggle room to break through that molecular attraction. But what if you dump so much heat that it breaks through it? That's just gas. But here's the deal. What if you put enough pressure into it that volume per, basically molecule per volume is the same as a liquid? meaning you have the same amount of molecules as a liquid, but you have no stiction as a gas. So your flow is smooth, laminar, and like, very low friction as a gas, but you have the density of a liquid. That's what it means to be supercritical. And yes, almost everything known to man has this graph, and generally you can achieve it. So CO2 is super optimum for that. So how the heck does this work? Well, it works on Brayton cycle, and it has no phase change. Whenever you hear about steam system, you are generally talking about Rankine cycle, which has phase change. Basically, liquid water goes to steam, steel becomes liquid, and cycle repeats. And people will say it's more efficient because you are not doing phase change. I have not found scientific validation of that. Let that be very clear. I have not found it. If you found something, please do share. But I have not found it. Like, which one is better depends on too many other variables. For example, what is your cold sink temperature? What is your heat source temperature? What is the scale of the unit? So the best scientific data I have is Brayton cycle makes sense for small units, and Rankine cycle is undefeated the moment you scale it up to like hundreds of megawatt, flat out. So that's why we use water, steam, and water again. Flat out. People have tried, let that be clear. People have tried Rankine cycle, Brayton cycle. And again, that's a jet engine. Air comes in, air goes boom, air goes out. The end. Air comes in, air gets compressed, fuel added, boom, high temperature, high air expansion, turbine, the end. So no phase change happens. That is Brayton cycle. But the moment you want to scale like 600 megawatt and you want like, okay, I turn it on, I turn it off after 10 years. Yeah, at that point in time, more and more data I'm looking into it is like, yeah, Rankine cycle is far more superior for that sort of requirement, where you have GG scale and just like turn it on and forget about it. So how the heck CO2 could be so more efficient? Well, the one thing that is absolutely important for CO2 turbine to reach that sort of efficiency is recuperator. So let's start our journey. So we take CO2, you pressurize the hell out of it. Now it becomes supercritical. Actually, you are feeding it also at supercriticality. It just goes high in pressure. Now it goes to recuperator. I'll explain what this does afterwards. Then it goes to primary heat exchange. This is your heat source. It could be solar, it could be nuclear, it could be waste heat from a steel plant. You heat it up. So now it has two things. It has very high pressure and very high temperature. Then it goes to turbine. Now here's the turbine. It's actually expander, meaning you put, let's say 100 bar into it, output would be only 20. This turbine consumes pressure, does not consume the heat, it consumes pressure. So you dump a lot of pressure into it, and a lot of pressure is lost. And again, that's what is converted into your electricity via generator, but you still have temperature. You like almost the heat wise, most of the heat is still there. So that heat goes into your recuperator. Recuperator preheats the incoming stream from the compressor, and then recuperator dumps the remainder heat into cooler, basically the radiator that you have outside. Now here's the deal. You might be like, okay, why do that? Why not just close it? If you close the system, energy will not have a flow path. Energy must flow from hot end to cold end, then you can extract energy. If it does not go from basically hot end to hot end, it does not work. There is no flow. It will just heat up in pressure and go boom. So it must have a cold sink. Now cold sink here in principle can be at very high ambient and still be functional. It will not require you to dump a lot of heat. A simple example of this would be your car radiator. Back in the old days, car radiators used to be under 100 degrees Celsius, water's boiling temperature. But here's we realized that we can make radiator very small and engine more efficient if we can make it hotter. How do you make something hotter? Increase the pressure. So water went from like 100 degree system to 150, and some can go even higher than that. That allows your engine to work at much more efficiently, and even if it heats up, the water is at 120 degrees Celsius. It can dump heat even in an Indian ambient of 60 degrees Celsius because T delta is so huge. So here you get huge T delta. So that's how the cycle repeats. You take main compressor, you dump GG amounts of pressure into it, you dump remainder amount of heat into it, then you do the main heat source and turbine converts it into useful work, and the cycle repeats. So this recuperator is the primary reason why CO2 turbine in paper can hit give or take 50% thermodynamic efficiency. So that's the whole point. And again, hot ambient, but be mindful, we are talking about CO2 at supercriticality. So how the heck you make sure the heat exchangers work? We have to use printed circuit board. And yes, if you have watched my Bangalore trip one, I have got my hands on, like I touched that, my hands on into it. Yeah, it is dense. Like it is something that you can trust that it can handle like 100 bars of pressure without mixing those two fluid. And it's like, I got this. Diffusion bonding, I got this, me good. So it's very good. Now let that be very clear. Compressor does take a lot of power. Now, Brayton cycle does compress fluid far more than what you have in Rankine cycle, because in Rankine cycle you do not just have flow water into the boilers, you pressurize that water like bonkers. Like you could be looking at, let's say, 600 megawatt output. You could easily be looking at 60 megawatts of energy consumption just for pump to pressurize the water. Here it would be 20 to 30% of that. And again, basically a jet engine, compressor consumes so much energy. That's why they are so goddamn hard to start. It's like your starter motor has to create enough power for the compression system. So that's the difference. That's why I'm not sold on the fact that it is efficient because it's a Brayton cycle. It's like Brayton cycle has heavy energy hungry compressors, all of them. So that's like, and again, compressing liquid, you're not even compressing, you're just increasing its flow rate. That's far more optimum energy wise. So that's why I'm not sold on that part. That cycle is more efficient. I'm sold on the temperatures and pressures are more optimized and recuperator works. So that's the whole point. And again, in this design, you have both of them on single shaft. We call that turbo expander. So you have a compressor on one end and expander on the other end, turbine. It is used in oil and gas industry. Many designs have them as two separate units. Some of them have in one shaft. Depends on your design. So that's the topology we are talking about. The cycle will remain the same, but will it be single shaft or two different units? That depends. So what did the China do? Well, China made some bold claim. Now, you know anything about China? China makes bold claim every Wednesday. So they are talking about world's first commercial CO2 turbine. What does that mean? That simply means they are running the meter of that steel plant in reverse. It's almost like once you have the solar plant in your rooftop, it runs your meter in reverse. That's what's happened. It's not a power plant where it's like, okay, I'm consuming fuel, making electricity and selling electricity. That's not the point. It's consuming waste heat and reducing the power consumption of the steel plant. It's not commercial. It's more of like, commercially viable because it's reducing your running cost. That's why it's basically energy recovery system. So we are looking at 15 megawatt turbines, and they have two of these puppies, 30 megawatt of total energy recovery system. Now, again, all the percentage they have talked about does not make sense because they are not specifying percent against what. Because it's almost like same thing saying HVDC is 50% more efficient than, high voltage AC line energy transmission. Does that mean AC line is only 50%? No, it simply means AC transmission line generally loses 3% energy per 100 kilometer. Compare that to HVDC, which only loses 1.5%. So that's why percent I'm not going to talk about it. The numbers are too vague, too hulululu, too liquid to make sense. We know 15 megawatt one turbine, 30 megawatt total. That's the only thing we know. And the waste heat of steel plant is huge. You are looking at 700 degrees Celsius. So that's some serious heat. Now let that be very clear. This is common in few industries like cement industry and steel industry, where if plant is big enough, they actually invest into energy recovery via steam turbine. So they had a steam turbine there. They replaced it. So what they are doing is what we classify as low risk grid tie, meaning can we do this? Like, can we actually do this as a power plant system, meaning just turn it on and forget about it for 10 years? They are doing that. Integration testing. Now, the most important, I do not care about the efficiency and all that. Those things are variable, too many variables. But the most important thing that is missing are what are you using? How are you getting electricity out? Because RPM is very high, meaning you can't direct drive a generator. So if you have to use what we call high RPM generator, turbo generator, hyper turbo generator, these will create very high frequency electricity, meaning your normal turbo generator that is used in power plants, they are 50 hertz or 60 hertz in America. And RPM is not high. They are generally 1500 or 3000 RPM, two pole generator. Four pole, the higher the pole, the lower the RPM. So hydro dams have very low RPM. Coal can easily have 1500 or 3000, but generally you do not exceed that. These things start at 20,000 RPM. So I do not know what they are using here. So are there generators that can work at those sort of stupid RPM? Yeah, look into F1 energy recovery system. That's like, bruh, that's Wednesday. So, but penalty is the electricity has bonkers frequency, meaning I don't even think it will be at 400 hertz. I'm pretty sure it will be in kilohertz. Penalty of that is you need bonkers size of inverter. Basically, that will take high frequency AC, convert it into DC, then make grid tie AC output from it. So, and again, inverters that are size of like 15 megawatt is expensive. The single most biggest inverter I think is used in wind turbines. They are generally 14. General Electric has that highlight turbine. I think that is the largest known. Again, I could be wrong, but if you found something, do tell me. I think that's the largest. So 15 megawatt single turbine inverter, it's very expensive. And like, don't we have solar plants that have more than that? Solar plants never do this sort of stupidity where they have one inverter that size. They generally have strings. Each string could be 1 megawatt, 2 megawatt or something like that. They generally, it's unwise to have one inverter that is 2 gigawatt. And again, nobody can afford it. So I do not know what they are doing here. What is the second option? Second option is you have a gear box. So they said that they had a steam turbine. So what if they want to use the same generator? So I had grid synchronous output. It would require a planetary gearbox or something similar where you will reduce the RPM. That is the most important part that is missing. And that's the most unsettling part. Again, my gut feeling is they are using inverter. My gut feeling says that. So what's the reality of the situation here? Well, it's great on paper. Again, if you watch my old videos, they're like, yo, this is going to be awesome and all that. But yeah, it has too many unknowns. The more I study about it, the more I learn about things. It's way too many unknowns. And it can work dry, GG. But it reduces efficiency, meaning it has the same problem as solar panels in India. It's like it's rated for 25 degrees. India is not cold. And in the CO2 papers that I'm reading, it's 20 degrees Celsius. That's winter for Indians. So yeah, we have to design things for 60 or 70 degrees Celsius, not 20. So, and again, they are saying like for every 5 degree, it will lose 6 to 7% efficiency. I'm like, bro, by that time, it will be useless compared to steam system. So again, it can work dry. That is sorted. It just, will it be efficient if the hot ambient is default condition of the radiator? I do not know. I have not seen any data on it. Second, high RPM. High RPM has issues, and it's a law of physics issue. You cannot cheat it, bypass it. You have to deal with it, meaning you have to spend money on it. So bearing reliability becomes a hassle. So how do you seal it? Well, that's up to you. Bearings, generally you can have magnetic bearings, expensive AF and fragile as hell, meaning you have to make sure that electric circuit does not fry, and you generally have to have a backup bearing in case the magnetics go kaput. So bearing reliability, again, bearings have a very simple rule. Lower the RPM, the longer the lifespan. Meaning, in a core power plant, 3000 RPM bearings, they only open it up like every 10 years or shut down. That's like, okay, let's check it and validate it or throw it away. It's like, again, if it's running for 10 years, you generally have done your ROI on it. So bearing reliability is inversely proportional to the RPM. So having stupid RPM, 20,000, 30,000, bad. Another aspect, it can't direct drive turbo generator, meaning if you have a coal power plant, okay, you want to swap it, you have to throw away the turbo generator, and they are very expensive, and that's not acceptable. And be mindful, turbo generator works because it has inertia, and that's why your voltage grid remains stable. Without having that, it's like, that's a big issue. Grid tie inverter or those sort of scale, like imagine like you really want to do something big, like 600 megawatt, which is normal for India. A turbo generator that is, one turbo generator that is 600 megawatt. Yeah, grid inverter that is 600 megawatt. The best I can see, you can make it like 220 megawatt, like each phase goes through one inverter. But yeah, that's expensive AF. And gearbox, which again, I know the American colleagues are working on that. They have a gearbox, which again creates the issue of chatter. So, unknown. Seals hit high RPM. Can you seal something on a spinning shaft? Of course, your car has basically refrigerant on one end and an open shaft to the ambient air another end. It does work, but again, RPM is not that high and the pressure is not that high. Here you have bonkers RPM and bonkers pressure. So this sort of like, dry gas sealing or this sealing, can it work? Of course it can. Can it work for 10, 20 years? That's the question. So, and again, all of these problems can be solved. It's just that question is, by the time you solve all of these, would it be worth it? It's like same question as brain damage of Hyperloop. Can you make Hyperloop? Of course you can do that. Should you make Hyperloop? No, just make high-speed rail. It will give you 10 times the yield. So that's the whole point. Stupid RPM and a high pressure is like, again, look into jumbo jet engines. They are low RPM, surprisingly low RPM. So, and do we have alternative? That's the core question. Do we have anything else that can replace it? You have ORC, meaning organic Rankine cycle. It's a known system. I even covered one of them in my expo visit. It's a known system. Buy it and forget it. Meaning you can pick up a phone. In all countries, you will have at least 2 to 3 suppliers, and all of them can give you, yeah, we have been running for 30 years. It's done, it's sorted, it does work. It's only 30 to 35% efficient, but it's a known system, meaning you do not have to worry about it. And yeah, that's a done deal. Another aspect, what if you want coal power plant to be more efficient? Make the steam itself supercritical. Yes, it will make your metal more expensive. Yes, it will increase the cost of the plant, but it does work. And again, you maintain your basically same hardware. Now, what does it mean? That simply means you are reducing the coal burn rate. Meaning generally they do not make supercritical system to make more power. They generally do it so they can consume less coal. So turbo generator will still remain 600 megawatt. RPM will remain still 3000. It's just that they're gonna consume far less coal to give you the same output. So that's the reality of it. It's like, can we do all of this? Of course. It's just that, can we do it and still make it logical? So what can we expect in the future? Well, reality is tech needs what we call long-term field validation. There are certain things that you cannot define in a lab, meaning everything works in a lab, nothing works in reality because of this long-term field validation. And nobody's gonna use CO2 for nuclear. Like, don't even think about that. Nuclear will require, oh, you think it will work for 10 years? Come back to me after 10 years. And again, they have to do that because oops cost in a nuclear, ask Chernobyl. Oops cost in a nuclear system is brutal. Ask Fukushima. So fundamentally, we have learned the hard way. You shall not oops a nuclear system. So fundamentally, you're not gonna touch nuclear unless you have long-term field data. And I mean, 10-year will not even be serious. They will be like, okay, 20 to 30 years maybe. So that is there. Another aspect is corrosive nature. Now let that be very clear. This is bit less, but bit more. From normal steam, corrosive nature is worse. But from supercritical steam, it's bit less. Corrosive nature is there. But again, it's an issue. We know how to deal with steam. We know this. Like, we got this. Like, if you pick up your phone, hey, General Electric, I need a steam turbine. They're like, bro, I got you, fam. I got you. We know how to make the metal that can handle it for 30 years or 40 years. We good. We got this. We don't got this for CO2. Again, the technology is not sorted yet. Again, long-term use. So corrosive nature is unknown. High RPM, it's not long-term stable prospect. Like, law of physics says, if you want something to last longer, thou shall not use high RPM. So let's see. Again, let them make it. It's not that it can't be done. Like, there are a lot of chillers that use that. But again, they are small units and they have magnetic bearings. And even they do not have this sort of, they are refrigerant, but they do not have this sort of bonkers pressure and corrosive nature of the liquid. So it is there. So for energy recovery, ORC is cheaper, mature, and ready to go. Like, you can just buy it, install it, forget about it. You can do steam also. And again, steam people prefer to do that because again, grid synchronous inertia. So that is there. And thermal power plant is already under pressure from solar power and wind power. Solar power in India is getting horrifyingly cheap, meaning coal power plants is like, we can't increase the price, but coal prices are going up. So that becomes an issue for them. And wind power is also coming close. So that is there. And this whole idea of like, supercriticality steam. Yeah, this is India's plant. It's in Jharkhand. We have it. I can go to and visit it. It's there. Like, we got it. Take it and go. Germany is like, bro, we had this for like 20, 50 years kind of deal. Like, we got this. Like, right now, world's supercritical steam generation is give or take 600 megawatt. Like, we got this. We know this. So fundamentally, and the fact that you are getting grid inertia, which again, without grid inertia, look into any and all news cycles on it. You will find, oh, UK kaputted itself. Oh, France kaputted itself. Oh, Texas kaputted itself. Oh, China had this area going kaput itself, because without grid inertia, you do not have stable electricity. This is the most important part of grid. I have no idea why people think inverters can replace it. It's like demand. When you have high demand, RPM starts to grow. Not the voltage, RPM starts to go down. And because you have massive puppies, like turbine itself could be 100 tons or hundreds of tons, and the turbo, and those are in one shaft, it's spinning, it will not slow down. Law of physics is like that. You cannot slow it down. It will slow down slowly enough that computer will like, my RPM supposed to be 3000. It went from 3000 to 2999. Yellow alert. 2998. 2905. It's like, okay. Increase the steam pressure. Tada, your frequency starts to go up. What happens? Somebody disconnects the load. Tada, your generation starts to bounce back. Again, RPM will start to go high, and your steam system would be like, my RPM is supposed to be 3000. Why the heck is 3001? Why the heck is 3005? Okay, shut down the steam pressure. So that's how it elongates microsecond spikes into seconds, where you can like, I got this. Oh, and be mindful, all generator act as a collective. All generator. That's why we had call it grid sync. And this whole delusion that people have, what if we have black box technology where we like, give our national grid to someone else like General Electric and all that. I'm like, do you want to be like Venezuela where they can shut off your system? So, oh, and to give you a context, how important grid inertia is, half of European countries are realizing that all the old coal power plants they turn on, use the turbo generator, put a big ass flywheel on top of it, run it as what we call synchronous condenser. So it provides the grid inertia for all the solar and wind. So this whole idea of like, okay, inertia not being important, without inertia, you do not have a grid. Like we think we use AC for like, the voltage up and down. Yes, but the biggest advantage of AC is this, grid inertia. And again, that's why, like, if Germany, would they switch from their supercritical, which is expensive, let that be clear, from their supercritical to like, CO2, I cannot see even a single reason, because this does work. This does cross 40% thermodynamic. Like India, we have it. We got this third party tested. They are almost touching 50%. 45 is like, you can do that. It costs a lot, but you can do that. So 40 and to like 5% theoretical, which mind you, nobody has actually achieved it. And not to mention, you do not have grid inertia. It's like, what's the point then? And again, if you're like, okay, I want a small energy recovery system, use ORC. Take it and go. So fundamentally, the likelihood of this technology catching up is low. Like, I get that why people are so attracted to it, but it's like too many missing variables. And it's too hard from economics point of view. It's like, can we make something that can work at high RPM? Of course we do. That's why I said look into F1 a thermal energy recovery system. I don't think they have in this season, but they used to have that. And those can work at 100,000 RPM. It can be done. It's just that cost becomes lol. And I do not like the idea of cost becoming lol. So that's the whole point. So this was my presentation on basically China's whole hype and the world hype about CO2 supercritical system. Hopefully you have liked it, learned from it. In that case, please see the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my assessment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.